Hi, welcome to the Calculus 3 lecture series, and we are in the unit partial derivatives. This is the lecture number 6 in this unit, and in this video, we're going to talk about directional derivatives. Okay, and then we're going to introduce a new notation. We call it the gradient of functions here. Okay, so now let's getting started, and let's go to our worksheets here. Okay, so before we talk about the directional derivative, let's do a very brief review. Then you can see, how is this definition was derived. Okay, so like, in the calculus 1, right? So when we talk about the derivative of f prime x, or like f prime, like we said f prime x here. So basically, so what we did here, so this is your functions, right? So we said this is f of x, and then you will have x here, and then you have x plus h here, right? So we try to find the derivative here. That means it's the tangent lines here. So what we did in the calculus 1, we say, hey, the f prime x, right, or the specific function is x0, let's say x0, this will be equal to the limit h approach to 0. Now here you have h here, this is x0 plus h minus f of x0, right? Just like in here, we say, hey, we try to get the h smaller and smaller. Then we want to see what is the slope, getting close to, right? So this is the basic definition we have at the calculus 1 here. And now in the calculus 3, in the sections, in this section, the section number 3, when we talk about the partial derivative, if you still remember, right? So we have the z, we say the z is a function of x, f of xy. Then we define the partial derivative of x is x0, y0. So what do we say about it? We say, hey, this is a derivative to the x variables, right? So we say limit h approach to 0. Then we say this is h. Then we say x0 plus h, and the y0 minus f of x0, y0. That's how do we define as the partial derivatives with respect to x. That means you treat the y variable as a constant. So the same way is here, right? So we say the f of y, x0, y0, we say this is the limit h approach to 0. Then you say this is f of x0, y0 plus h minus f of x0, y0, right? So, if you still remember, so we say the f of the partial x's here. That means you fix, so this is the, you fix the y value, then you take the derivatives, right? So this is the one, you take the what? You take the derivative along what? Along the x-axis here, right? And then the same way is here, right? So like this is f of y. So we say, hey, what is this one? We say this is the one, you take the derivative along the what? Along the y-axis, right? So basically, like in here, if you still remember, we have the graph here, right? So like if in here you have some type of the space, like in the, in the R3, then when we talk about the f of x, so we said, hey, here basically you have something like, you fix the y's, right? So the y is equal to a certain number, then is touch this surfaces here, right? So then you have a curve on this surface. Then when you take the derivative f of x, that means you are taking the f derivative derivative in this direction, then the f of y is you take the derivative of this direction along the, like when you do like the, here you will have like a, so we say here, you know, you will have some like the, maybe the curve over here, right? So that's what you find the tangent line of this curve on the surface. So when you do a cross section, when you try to have like a plane intersect the x-axis and y-axis, so then the tangent lines on the top of these curves here, the f of x is one along the x-axis and the f of y is along the y-axis. And now in here, okay, so now in this section, we're going to talk about the directional derivative. Okay, so in here you have x and y, right? So right now in here, let's take a look for this ones here. So you have some type of the surface here, but instead of, so right now that means I'm going to, you know, so I'm going to try to find a derivative in this directions here. And this is, I said, give me any u's, right? So in this directions here, and then I want to find, so basically still, you know, you try to find the, so you have like a, you know, like you find like a kind of the plane, right? So you find like a plane that intersect at this direction, then they create a curve on the surface, then you try to find the tangent line along the, for this curve along the u's, right? Okay, so this is how do we derive, you know, we said the directional derivative is here. So because of this directional derivative, so it's related to what? That means I'm taking the derivative respect to a certain vectors, right? So vector u's here. So the notation we use this is du, right? So f of x0, y0 here. Okay, so first let's understand meanings here, right? So this is a du. That means right now I'm taking the derivative along the path. I'm going to this direction, the direction of my vector u's here. So it's just the same. So if the u, right? So if I say the u is a vector, right? So I can say it's a and what? A and the B's here, right? So that means if you break this one out, so this is A and this is B's, right? Okay, so you will say this is A, this is the B's here. So the directional vector, so just same things. You know, you take a look at the partial. If you partial to the x is x0 plus h, partial to the y is y0 plus h. So in here, now, that's the same way. So we say, okay, I'm going to this direction, the u directions, right? So if this is the, so I will say the limit h approach to 0 again, right? So what is the h here? H, that means is in here, right? So the h, that means in here. That means when I approach to the h approach to 0, just like you approach from here. So the h approach to 0. So if this is my h directions here, because we said we wanted the u in here, the derivative for the vector u, the vector u has to be a unit vector, okay? Okay, so vector u has to be unit vector. So when this h, right, so if it's a unit vector, then this length here will be what? This length will be HA, and then here will be what? HB's here, right? So when you go to the u direction, you really think, you're really doing here is x0 plus AH, and the y0 plus BH, right? Then you minus f of x0, y0. This is how do we define the directional derivative. That means I am going to take the derivative along this specific path of the vector. Okay, so now if you take a look here, so this is the one. This is how we defined, right? So we say okay, so we said let u and b u equal to the AB is a vector. So this is very important. The u has to be a unit vector in the xy planes here. Okay, and then the directional vector is defined as du, so it's x0 plus ah plus y0 plus bh. So like in here, this graph is, you can see very well. So that means you basically, you have kind of the plane, you cut this, this light blue area is your surface, right? So then they generate this golden curve, right? So they generate this golden curve. And now you have the x0, y0s here, right? So you from this point, at this point, right? So this is x0, y0, z0s, right? And then now you want to find the derivative, right? So basically you want to find the derivative of this golden curve at this point here. So that's why your h here is approach to 0. So this is h. Because of u is a unit vector, if the hypotenuse is h, so then this side is ha, this side is hb. So that's why we have the x0 plus ah plus y0 plus bh here. And so this one will be minus f of x0 and y0 here, okay? And then this ones here, you can, you can prove it easily. So the du f of x0, y0. So in here, you can say this one's here. Okay, so you can really say the g h here. So the g, you define the new function, right? The gh will be the x0 plus ha and the y0 plus hb's, right? So this will be a function, right? So this will be a functions of the, h's here, right? Then we say the g prime. So the g prime 0 will just be equal to, you have a limit h approach to 0. So here we set a f of what? H here, this is f of x0 plus ha, y0 plus h of the b minus f of x0, y0, right? So now, because the x here is x0 plus h0, so you take the g prime h here. So in here, because I really mean is x0, y0. So g prime h here, the first you need to take the partial, right? So because of both of them, so you have the h, so the f of x is here. So that's why you take the partial. And then after you take the partials here, you need to do what? You do the chain rules, right? You take the derivative to h here. So what is the chain rule? Is a. Then the same way is here, right? So you take the partial for y, because y is a function of h of b. Then your chain rule here is b. So that's why I have the du of x0 is equal to, is your partial derivative dot and the times the a and the partial derivative of y times the b. So basically, if you want, you can find these ones here. This is x0, y0. If you treat these two values as the vectors, right? You can say this is dot a and the b's here. Okay, so that's why the next things we're going to talk about here. So like in here, right? If we say if u is along the I, right? So now what is du fx0 mean? So if the u is along the x-axis, that means the u is equal to the 1, 0s, right? So the du will be just be what? F of x, x0, 1, 0 times 1, and the b is, so this is f of the y, x0, y0 times 0. So this is f of x, x0, 1, 0. So this is the partial, right? So this is the partial of the, okay, so this is a partial derivative at the x0, y0 here. Okay, so let's try to do a mechanical ones here. So let's say find the directional derivative in the direction of the u. So first, let's check to see u, the length of the u, right? So the length of the u, so this is 1/2 to the square plus negative 3/2 to the square. So this will be 1. So I know the u is what is a unit vectors here. Okay, so we know that U is a unit vector, and so because U is a unit vector, then I can use the what we just derived. So I say, okay, partial x here is what? Is 2x y squared minus y cubed. Partial y here will be what? Will be the 2x squared y minus 3xy squared, right? And then I plug in what? So the du's here, right? So the du, the partial derivative of xy will just be the f of x times the a, so will be the 1/2 of 2xy squared minus y cubed, and minus, the b is here is -3 to the 2, the plus b is negative, and then the f of y, so it's 2x squared y minus 3xy squared. So you can combine or just leave like this. So this is what we say is the directional derivative. So it's how fast rate of the change. So now if you're any given x0, y0, you can just plug in here, right? That's basically tell you the given points, right? So the how fast the rate of the change, if you're integrating along a specific path, like for example, this is what we say if this is the specific path for your vector use here. All right, so now a while ago, okay, sorry here, too fast. Okay, so a while ago from the previous one, we said, we said the du, we said the du f of x0, y0, we say is use partial x0, y0 times a plus f of y x0, y0 times b here. Okay, so now we have defined here, so we defined so this is the definitions, right? So we defined this, we call the del fx0, y0, we define the vector del. What is this vector? This vector is the partial x, partial y for any given points here. This is what we call this a del. So this one pronounced as del. The gradient, we know is a very important vector here. So in here, that's just like we say here, that this is f of x times y. So you really, if you can change that to the f of x, x0, y0, f of the y, x0, y0, and the dot product ABs, right? Okay, so this is a very important formula here. So for this ones here, the du, the directional vector, will be equal to your dot product. Okay, so the next ones here, we have also a very, very important series here. We tell you, if f is a differentiable function of 2 or 3 variables, then the maximum value of the dfy is del f of x. And when it occurred, when u has the same direction. Okay, so what's that mean? Because I know here, right, so the du, right, so du f of x0, y0 is equal to del f of x0, y0 dot product u. So we know the dot product, right? So what is the dot product? We say this will be the del f of x0, y0 times u and cosine theta, right? So cosine theta is the angle between these two. So I know cosine is between 0 and 1, so the largest of value is when cosine is 1. So when is cosine equal to 1? When the theta equal to what? 0 degree. That means you will get the largest rate of the change on the direction of the u if the u is on the same direction of your gradient vectors here. And what is the largest value? Because the u is a unit here, it's once, right? So the largest value, so that's why the largest value is del f of x here. Okay, so that is like so is what that means here. That means, you know, like if you are in the mountains, right? So, and if you are in the mountain and you want to like drop a ball to see how fast the ball going to rolling down, which way is the fast path. So the ball going to rolling down. So if here is your mountains, right? So if here's mountain, you have a ball here. You drop the ball to see which path the ball going to coming down to the mountain. Which way they're going to go? They're going to go to the gradients, right? So also that's why here this is kind of like kind of intuitively true. So your gradient vectors here, right? So that's the fast path. It will be what is a perpendicular, right? It's a perpendicular to your level curves here. It's just like we know the level curve is kind of like a contour plot, right? So if this is a contour plot in the mountains, right? So we kind of intuitively we said, hey, if you want to go up the mountain or go down the mountains here, right? So if you want to go up the mountain, what will be the steepest increase? It will be you go straight up, right? So that's why, you know, we say this will be the perpendicular to the level curves here. Okay, that's one very, very important results we have. Okay, so now let's take a look here. So let's try to do some mechanical part. Okay, so let's say find the gradient vector. This is very easy. So I know the partial is what? It's y, e, x, y. Then partial of the y, so it's x, e, x, y, right? So you take the derivative of e, x, y, don't forget the chain rule. So the gradient is del f of x, y, so it will become a vector. So this vector will be y, e, x, y, and the x, e, x, y, right? So that's what we call the gradient vectors here. Okay, so the next things here, so let's say find the directional derivative at f of x, y, z in the direction, at this direction, at the point 2, 1 pi over 4. So first, let's check to see, you know, is this one. Okay, so let's check to see is this one is the unit vector or not. So let's see the length of the u. So the length of the u is what? This is 1/2 square plus -1 square root of 2 square plus 1/2 square. So this will be 1/4 plus 1/2 plus 1/4. So it's 1. So I know this is, so this is good. So this is the unit vectors here. Okay, so now let's see here. Okay, so the f of x, right? So f of y. Okay, so let's okay, so let's take a look f of the x here, the partial for x here. So the partial for x, so here be y sine z, correct? Okay, then the partial for y here, it will be x sine z. Okay, and the f of the z here, so what is the f of the z? The z is a cosine, so it's xy cosine z here, okay? And so now I set up, because we are doing at this point, right? So when at this point, when the f of x at 2, 1 pi over 6, what is the, this one's here? This one will be 1 times the sine pi over 6. Pi over 6 is 30 degrees, so it's 1/2. And this is f of the y, 2, 1 pi over 6. So it's 2 times 1/2. So this will be 1. And then f of the z here, okay? So f of the z is here. It will be xy. So 1 times 2 is 2. Cosine will have square root of the 3 over 2. So this will be the square root of the what? Square root of the 3's here. Okay. So now we do the same thing. So this is my del f, right? So the del f at the 2, 1 pi over 6. What is this del here is 1/2, 1, and the square root of the 3. Correct? And so I know that the directional, so this is in the R3, right? So the directional du, so this is the direction in the R3. So the du f of 2, 1 pi over 6 will just be equal to the del gradient vector 1/2, 1, and the square root of the 3, and the dot product of what? Dot product your your vectors here, right? So this will be 1/2 negative square root 1 over square root of 2 and 1/2. Okay, so if you do that and so the final answer, it will be 4. And this is 1 minus 2 square roots of the 2 plus 2 square roots of the 3 here. Okay, so let's take a look at number 5. Okay, so let's say now you have 3 variables, f, x, y, z. In fact, we're in R4 because this is if you let the w equal to, right? So it's xy squared plus yz squares here. So let's say, what is the maximum value of this one? If I take the directional derivative of this function at the u's here, right? So we know the maximum value we just derived. So what is the maximum value of the du f of so what is the maximum value of the 1, 2, 1's here? What is the max here? So we say this max has to be the del value of the f of the 1, 2, 1, correct? Because del and u has to be into the same direction. Okay, now let's take a look at del f. Del f is the f of x, f of y, f of the z's here. So the f of x, this is y squared, and f of the y, this is 2xy plus z squared. F of the z is y, right? Okay, so now we know this is a del, so the del f, so this one will be the del f, the del f 1, 2, 1's, right? So you just plug in the point 1 to 1. So what is here? Y squared. So the y squared, so basically y squared is what is 4, right? Y squared is 4. And then like the f of y, so it's 2 times 4 is 5, right? And then the last one is y, right? So the y, so sorry, 2z, so here has to be 2y, so it's 4 here, right? Okay, so then this one is just the square root, so the 4 squared plus 5 squared plus 4 squared. So what is here? So this one will be the square root of the 57. So I know the maximum value of the du f of 1 to 1 is going to be the same direction as the u's, right? So that's what we proved. That will be the del is the length of your gradient vectors here. Okay, and then they say what direction u give the maximum value of the du f e to the 1 to 1. So we know the u, so u has to be the same directions as the what? The same direction as the gradient vectors, right? So it has to be at the same direction as the gradient vector at 1, 2, 1, right? So the gradient vector at 1, 2, 1 is 4, 5, 4. And I know this is not a unit vector, but I also know the length of the gradient vector is the square root of what? 57. So now I can define the u. So u will just be what? So u will just be 4, and then the square root of the 57, 5 square root of the 57, and the 4 square root of the 57. So that means if the u has to be at this direction. But now you divide it by the length of here. That's what will give you what the unit vectors, right? So that means this is the unit vector. The u has to be union vectors here. Okay, now let's take a look at the C. Let's say that now I'm going to go to the V in the 1, 2, 1, where the V is this directions here. Okay, so if this is the directions here, so let's first check to see V is unit vector or not. So let's see here. So this is a 5 over 6 to the square plus 1/2 to the square plus the square root of the 2 to the 6 to the square. So this will be 25 to the 36 plus 1/4 plus 2 over 36. I'm getting the 36 over 36 is equal to 1 here. Okay, so now I can do that. So I know the dv f of the 1, 2, 1 will just be what? Will just be the del f of the 1, 2, 1 dot product of what? Dot product of 5 over 6, 1/2, and the square root of the 2 over 6, right? Then the del, we know the what is the del, so it's a 4, 5, 4, then dot product of 5 over 6, 1/2, and the square root of the 2 over 6. And then if you multiply that out, so this will give you the 35, okay, plus 4 square root of the 2 and over the 6. Okay, so that this will be the directions, right? So this will be the directions when you go under a different path V's here. Of course, we know that the largest path is the largest rate of change is 50 square root of the 57th, right? So this value definitely less than the square root of the 57. All right, okay. So now the next things here, we're going to, we're going to kind of expand this idea to the, like for the R4. Okay, so let's try kind of refresh this here, right? So in the R3s, right, we said Z equal to the F of XY here, correct? Okay, so the Z equal to the F of XY here. And then we have like, so for the level curve here, right? So the level curve, like F of X equal to K, F of XY equal to K. It's kind of like, remember, we talk about like, this is like the contour plot like this way, right? So this is the contour plot, right? Okay, so now if I have a point, right? So if I have a point here, so if I have a point here, this is x0, y0. So as we know, when this point, right, if you want, let's change it to maybe make the point not like a parallel to y. So okay, so let's see here, if for example, here, right? So I have a point here, right? And this is my point, I have a point here. So this is the point x0, y0. So I know what is the faster, the rate of the change from one level curve to the other one, we say is in the del f of x, right? So it's the we said it's f of x to the x0, y0, and the partial fy to the x0, y0, right? This is what we say is going to be the, the fast way. So that's basically, so that means it's kind of like so this will be your gradient functions, gradient vectors, right? So the gradient vector will be perpendicular to the what? Perpendicular to the level curve. Okay, so now, in here, we do the same things here. Now I expand it to the R4s here, okay? So now let's see here, we have the exact same directions, the results here. So now if I plant to the R4, so that means I have a W is equal to the f of x, y, z here. So instead of the level curve, we have the level what? We have we call it a level surface. So the level surface, that means f, x, y, z going to equal to a constant case here. Okay, so this will be a surface. So this one drop back to the, so this is the surface at the R3, right? So we drop back to the R3, we can visualize it. Okay, so now if I let C be any curve in the surface S here. So we said this is level surface. Okay, let's say that this is level surface. If I have any curve in the S, now we can write a parametric form. So we can write C as is kind of like a curves here. And this one will be, you have some X function with T, Y function with T, and the Z function with T, right? So this is what we define the parametric equation. Then the same way we say the del F here, right? So the del F here, okay, so let's change a little bit. Let's change this one to the capital F. So let's not get confused, right? Okay, so let's to the capital F here. So the level surface is here. This will be the capital F here. Okay. Okay, so now we say the del F x, y, z. So this will be a vector in the what? In the R3, right? So it's fx, fy, fz, right? It's the partial here. So the same ways here, right? So we said that if you take the derivatives, right? So so the derivative is here, the f of x here. So we said the same way. So it's del f, right? And times the dot product, the derivative of the r prime t's here. So this one's here, if you take the derivative of r prime t's, it will give you x prime t, y prime t, and the z prime t's here. Okay, the reason why I need to do that is because maybe I shouldn't skip the step here. Okay, so I shouldn't skip the step, and then that's will cause the confusions here. Okay. All right, so now I said that if I want to take the derivative of this, right? So I said rho f, rho x, right? Because then the x, it's a function of t, right? So then I need to do a dx, what, dt, and then plus rho f, rho y, and the dy, dt, then plus rho f, rho z, and the dz, dt, right? I would say, okay, this derivative is equal to zeros here because this is the case here, right? So then we also define the del f, right? So the del f is a partial for x, partial for y, partial for what? partial for z's, right? And so if you take a look here, this is what? This is the f of x, this is f of y, and this is f of what? Z. So the same way, what is here? This is dx dt. So this is x prime t, this is y prime t, this is z prime t, right? Okay, so that's why we know the here, right? So now I have this is del f. So I know the del f dot product r prime t will give you the above, okay? So that means in here, I'll say this one will be equal to what? Equal to 0, okay? So now, okay, so if this one equal to zeros, right? So now in particular point, so if in any particular point, right? So in any particular point, x0, y0, z0 here. So we know the f of del x0, y0, z0 dot l prime t0, it will be equal to 0. That means, okay, so that means I know the del f of x0, y0, z0 is perpendicular, to the tangent vector. R prime t0 to any curve C is here. Okay, so this tangent plane we can write as, so like we said, we have a point x0, y0, right? And this is the directions, right? So this will be f of x, x0, y0, z0, x minus xz0 plus f of the y, x0, y0, z0. This is y minus y0 and the plus. So this is the fz0, z0 on x0, y0, z0, z minus z0 equal to 0. So this is the plane. This is a tangent plane, right? So that's why I know, because this is the plane, right? So this is what? So what are those things? Those are the what? Those are the constants for the plane. So that's the normal vector for that planes, right? So I can write as the normal lines here, because those are the direction for the line. So that means the normal lines here, if I use the symmetrical way, so that will be xx minus 0, then the f of x, x0, y0, z0, and equal to y minus y0, then this is y, x0, y0, z0 equal to z minus z0, and f of what? Okay, so f of z, the x0, y0, z0. Okay, so how is this one related to R4? So R4 is level curves, right? So this is R3 is level curve, right? So these ones here, you have something, okay? So imagine these things here. Okay, of course, I cannot graph the graph of W's, right? So, but I can graph the level surface. So for example, this will be the level surfaces for this function. So what does that mean? That means, you know, the whatever, right? So this is the what? It's going to be perpendicular to this level surface. So this is the normal lines here, right? So this is a normal line, and that's why it's the same like the R3 when you drop to the R2. So this will be what? This will be the gradient factor, right? Perpendicular to what? Perpendicular to this level, what? Will be perpendicular to this level curves here. So like the same ways here, right? So I'm going to, so this is my level surface. So I'm going to have a what? I have a tangent lines, tangent planes here. And this plane, so this is the what? This is the normal line for that tangent plane. And that tangent plane, that's what is, this one will be perpendicular to the level surface. It's very similar like the level curve concept. All right. Okay, so now if you go back to here, that is what the whole things will try to tell you here. So this is the, okay, so if you take a look at this is in the, the R3 situations, right? So this is R3, z equal to the f of xy, right? So I drop to the R2 to the level curve. So that's why your gradient vector going to be perpendicular to the level curves here, right? So the same ways here, like in here, right? So that's what we say in here, the tangent plane, okay, of the S and the P has the equation. So it's the same way. So you see here, this is what? This is your gradient vectors. So this is a gradient vector. What happens to gradient vector? It's going to be perpendicular. What is S here? S here, this is the level what? Surface. Right, so in here you have W equal to the f of x, y, z. So you are in the R4. Then when you have level surface, you drop to the R3s here. But it's the same idea. The gradient vector going to be perpendicular to either the level curve in R2 or the level surface in R3. That's it. Okay, so now let's take a look here. Okay, so let's take a look at part number 7 first here. Now we can do the mechanical part of number 6 here. So let's say, hey, given the following level curve z equal to the f of xy. So let's say, which one could be the gradient vectors here? Which vectors could be the gradient vectors? So I know, okay, so I know the gradient vectors, they have to be perpendicular to the level curve here. So this one perpendicular, and then this one is perpendicular. Obviously, C is not, A is not. So we have B and D, both of them could be the what? Could be the gradient vector at that specific point, right? So it's B and D, so it's pretty straightforward. Okay, and so number 6 here is just try to learn what we just did a while ago. So let's say find the equation of the tangent plane and the normal line to this function at 1, 4, 1 here, right? Okay, so now I will say the f of x, y, z, right? So it's equal to, I move everything over. So this is x squared plus 2y squared minus z squared 4xyz, right? Z squared minus here, I think in here we have this one's here. This has to be have minus 4xyz here, minus 4xyz minus 16 here. Okay, so I think here there's a type error here, right? So here. Okay, so here this has to be x plus 2y squared minus z squared and minus 4xyz. Okay, so minus 4xyz. Okay. Okay, so be careful here. So this one's here. Let's change that. This is z squared minus 4xyz. Okay, so now the del f. Let's try to find the del f here, right? Okay, so the del f. So let's take a look. So the first thing is here, partial for x here, right? So partial for x. So what is the partial for x? Is the 2x and minus 4yz, okay? Minus 4yz. Partial for y, what is the partial for y here? Is 4y minus 4xz, okay? Then what is z here? Partial for z is negative 2z minus 4xy, correct? Okay, minus 3 minus 4xy. Then the f of x to the 1 for 1. Okay, so x equal to 1, so it's 2 minus, so x equal to 1, so 4 times 4 is 16, so 2 minus 16 is negative 14. Then f of the y, 1 for 1, y is 4, is 16. 16 minus 4 is 12. Okay, so the f of z, the 1 for 1, so z is negative 1, z is 1, so it's negative 2 minus 16, so it's negative 18. Okay, good. So I know my del f 1 for 1 is equal to what? Negative 14, 12, negative 18 here, right? And because this we know, based on the property we just discussed here, right? So these things here, just like in the R2, the gradient vectors here, did you see here? The gradient vector has to be perpendicular to your level surfaces here. So I know this will be the direction for my planes here, right? Okay, so now I know how to write the tangent planes here. So then the tangent plane will be equal to, that means my directions, right? So this is negative 14, x minus 1 plus 12, what? Y minus 4, then minus 18, z minus 1 equal to zeros, right? If you simplify it a little bit, so you will get 7x minus 6y plus 9z equal to negative 18. Okay, so now, so this is the tangent plane. Then we also say the normal lines here, right? So the normal line, like in here, take a look here, the line is in the direction of the gradients, right? So the gradient vector, this one will be the directional for the line. So we know the line need to have a point. So the point is 1 for 1. So let's put it into the symmetric form. So the line will be the x minus 1. So what is it? And here is 14, right? Will be equal to y minus 4. What is here is 12, will be equal to z minus 1. And here is negative 18. I guess you can simplify that and divide it by negative 2. So this is x minus 1, the 7. This is 1 minus 4, the negative 6. And this is z minus 1, the 9, right? All right, so that's it. So for the gradient vector, so the summary for this section, so what do we learn? So we learn the directional derivative. That means you take the derivative on a specific path given by a unit vectors here, right? So the way we do that, so this is the first important formula, right? So the du f of xy is equal to what? Is the partial x times a plus partial y times b here, right? Of course, u has to be unit vector. Then we also defined, we call this a gradient vector. So the gradient vector will just be the two partial, or like if you have 3 variables, 3 partial. So the gradient vector play important role. So we know for all the directional derivative at a specific point, the maximum value rate of the change is happen, if your vectors is the same direction as the gradient vectors. Okay, so that's the second part we need to know. Then the third part is importance here is that means, if in the R2, your gradient vector is going to be perpendicular to the level curve. If in R3, your gradient vector is going to be perpendicular to what? Level surfaces here, All right. So make sure you understand this graph and this graph mean. So basically, this one we just expanded out to the R4 situation. So when you try to find the level surface, is you drop back to the R3, and then we understand how to find the tangent plane, then how to find the normal lines here. The normal line, look here, that's the direction for the gradient vectors here. All right, that's it. This is very interesting, the sections here. And I hope that you get a good understanding what we're, we're covering these sections here. All right, that's it. It's nice to talk to you, and you have a good day, and looking forward to talk about the next topics here. All right, okay, bye.